Hello, my name is David. Today is June 12th, 2025. I'm a student at Appleby College and I'll be trying to teach and basically help with any type of physics. Throughout. I'll be trying to upload daily with covering all of this. But in case you're wondering what I will be covering, or uh, we'll just be covering the AP Physics one, basically, just consisting of that for any type of students that are interested in physics. This is more of an advanced version, and also if you're just taking the course in general and you're curious. Alright. So it consists of 8 units, which are subject to change. For example, fluids used to be electricity, and now it's liquids and gases. And then we have, so let's just list them out. Unit one, kinematics. Obviously, I'll be explaining all of these later on. Unit 2, forces. Unit 3, work, energy, and power. Unit 4, momentum, linear. Unit 5 and 6 are rotational senses. Unit 5 is basically kinematics, rotational sense. And Unit 6 is work, energy, power, but in a rotational sense, right? Then we have oscillations, which is oscillating up and down, like a spring, for example. And Unit 8 is fluids, so liquids and gases. All right, basic chem knowledge for you. And so this is just to get you familiar with the units and what the physics consists of. All right. So let us begin with kinematics and explaining what that is. All right. So let us begin with some basic key quantities of motion and kinematics. So motion and kinematics just refers to like movement and linear kind of motions within an object or of some sorts. So yeah, let us begin with the key quantities. All right, quantities. If you can't read, that is perfectly fine. I'll be reading out loud every single thing I write. And so yeah. So for the first thing, when it comes to quantities for motion and kinematics, goes to position. And but first, let us actually reference something that you will see throughout your whole physics and kind of like a fundamental basic. You might already know, but this comes down to linear and vector, right? And this is kind of an important thing to try understand about when you're covering kinematics. When you're first starting out, I had trouble with it as well. But linear just prevent basically it's just the linear motion, linear like just magnitude. Basically, it's a scalar type of unit, right? Just keep this in mind. Scalar, which just means it's kind of like number based only, right? It has no direction. It can be negative. Keep that in mind. That's a very important thing. Can be negative. For example, take the temperature. It can be 24 degrees or -7 degrees, right? That's scalar. It's just a number. It has no other value other than just what it represents. But a vector as magnitude. Magnitude is basically the number value I was talking about, and direction. And that's where it comes the key differentiation between vectors and linears is that vectors have direction. Right? If you watched Despicable Me, vector, magnitude, and direction. Yeah, well, yeah, that's what it means. Yeah, and I just learned that at the start of the year. I never knew what a vector was before. But yeah, now you know. So just a key example would be this: a line going to the right, 10 meters. That's the linear value. All right, let's draw a vector of it. So this would be the vector, the actual arrow would be 10 meters to the right, east. And usually you'll write the arrow at the top of the number, just like that. Let me make that a bit more clear for you. And so you have the linear value, the vector value. All right? So that's just a basic key understanding. We can move on now. So let's begin with position. What is position? Well, it's a vector. All right, there we go. Boom. It's an object's location and basically just all space, really, in space. So again, referring to this line we have over here, our position would be here. But remember, position has to be relative to something, right? So we have units for position, and this is basically called the SI unit, the standard unit, Actually, I'll write that down. SI unit. It's just the standard unit for the actual quantity. Okay. So for this one, it would be meters, and you'll start to notice it's meters appears a lot, and oh yeah, relative to something. Oops, sorry about that. Relative to something, as I mentioned before. Right? It has to be relative to something else, or you just have no position, unless you're like over here on like XY axis. Your position would be here. I don't know, 3 and 4. All right. That would be a position, but it's still relative because sorry, relating it to the y and x axis. So it's always relative to something, or else you kind of have no position. For example, in this number line over here, if my position was here, I mean, where am I? I'm 10 meters to the end point, right? I'm 10 meters relative to something else, and you can just circle this, boom, you have the radius. Anyways, moving on. So the SI units is meters, and this has a symbol of X. Here we go. Here we go. There. So just basic definition is that something, well, not definition, but just like explanation, is that something has moved if its position has changed, right? And that makes sense. If your position has changed, you have moved, right? You have done motion. You have done the actual act of moving, right? So if its position changes. Okay. So now that we have that out of the way, let us move on to the second key quantity. Let me just highlight this. There you go. So number 2, after position, we have distance. And this goes on with another thing called displacement, but I'll be talking about that after. So what is distance? It's very basic, but it really comes down to the linear and vector explanation from before. It's a scalar unit, all right? So scalar, it's just the length of a particular path, which is path traveled, all right? As a unit, meters. That comes down a lot. Now, distance doesn't. Oh, sorry. Yeah, it does have a symbol, but you should. Use it interchangeably with displacement, kind of. Usually it's d. Symbol of d. Just depends what you're doing in an equation. If it's linear, you'll use the linear symbols and so on. So don't get confused with displacement, obviously. But distance is just the actual length of the path traveled. So let's say, actually, I'll explain it in comparison to displacement. So that's the third unit actually, displacement. Sorry about that. And sorry if I sound nervous. First time doing this. I'm just excited. I want to help people out. That's basically my point. Displacement is a vector, right? So like I mentioned before, these are basically not they're not the same, but They are related. They are very similar. Just the difference is scalar and vector. So it's the actual change in position, right? Remember how we said the change in position refers to a movement or like motion? This is what the act is called. It's called displacing, right? If I have changed my position, it means I have displaced myself, right? And they're both vectors for a reason because it comes down to magnitude and direction, right? So same units, units, meters, and then the symbol. Um, this is where it comes down to is delta x, right? In case you don't know, delta is this triangle. It stands for change, right? And you can always expand this delta x into x final minus x initial. Or you can do x minus xo. And you'll see this in your formula sheet. Matter of fact, we can just go check the formula sheet. So ignoring all this, you'll see a lot of the time, right over here, we have distance, d. Okay. And it's used a lot, to be honest. But yeah. This is the formula sheet in case you want to get familiar with it. This is the official one. And there's also another sheet, but that comes with just basic measurements, and I will be explaining that too. But yeah, this is it. As you can see, it doesn't actually offer every single formula, but you'll be able to rearrange them, and that's kind of what physics is all about. It's a very algebra heavy course, right? And you'll get used to that. It's fine. You got this. And it can also be used as data, right? But mainly you'll be using this one. And delta x. Right? So if you still don't understand, I think a good example of this is looking at a track, right? A 400-meter track. So if you run a 400-meter track, you're running 400 meters, right? You run one lap, that's 400 meters. You know that, right? That's the distance you're running. You know, you run any distance, you'll get to that distance. Yeah. But the actual displacement, remember what position was? Position is the location in space relative to something. Okay. So if we relate the position to ourselves, our starting point, right, is 0 meters. This is our starting point. This is our position, right? Position initial. That's what it is, basically. Okay. So distance is still 400 meters here, right? Don't get that wrong. 400 meters. But now, what is our displacement? Okay. Try to answer the question. Okay. What is our displacement? So look right back here. Let me make some space so you can clearly look at this example. There you go. Right over here. Remember, our displacement is the change in position, which would be our final position minus initial position. But at a track, or at least in a 400-meter track, where do we end up? We end up at the finish line, which is exactly right where we started. So our final position, and this is very important to keep in mind, position is 0 meters as well, right? So this would be our x final, and this would be our x initial. But notice how they're both the same. Let's do the actual equation. Let's implement this. So our change in position is, the actual change in positions we have from final to initial. How much have we actually moved relative to ourselves or the track, really? And 0 minus 0 equals 0. So displacements actually end up being 0 meters. Right? So let's look at our number line. Right. Here we have 0. Now let's go 5, 10. I move all the way over here 8. And this is meters. This is all meters, right? So let's say I moved 8 meters, right? And then, I was like, I forgot my favorite ice cream. So I went all the way here. Doo-doo. All right, sorry about that. Yeah, anyways. Yes. There's a raccoon at my door. So, anyways, let's say we went 8 meters to the right. And then, yes, like I said, my favorite ice cream, blah, blah, blah. I forgot it. So I had to go 5 meters back. So what was my distance traveled? My total distance. How much did I travel? Right. I went 8 meters and then up. I went back 5 meters. So damn, I had to walk a whole. There we go. A whole 13 meters. But what was my displacement? Where did I start? I started here, didn't I? This was my x initial, my position. But where did I end up? Oh right, I ended up here at 3 meters, where my favorite ice cream was. This was my x final. So even though I traveled 13 meters, my displacement was only my displacement was only 3 meters. So yeah, keep that in mind. 3 meters to the right, east. Remember, magnitude and direction. So that's just a simple example, right? Okay, let's move on to. Wait, let me just move this here. Let's move on to speed and velocity. Similar to distance and displacement, these are both scalar and vectors. Okay. So number 4, speed. So this is the rate at which the distance was traveled. Okay. It's scalar. And it's units. Let me move this over here. Traveled. So speed is the rate at which distance was traveled. And it's units. Meters per second. Okay. And this is scalar. Now, velocity. This is the vector version. The rate at which position was changed. So this is relative to the scale vector units. Okay. At which position changed. Okay. So you'll start noticing a pattern that every scalar goes with other scalars and the vectors go with vectors. And once you understand, first of all, scalar and vector, which I explained right over here at the beginning, then you'll start to, try understanding all the differences between the different quantities such as speed, velocity, distance, displacement, position, things as that, The more you practice, the more you understand. And I guarantee you will do lots of practice, okay? Practice makes perfect. Remember that. So it has the same units. So same units. Both are meters per second. Uh, let's say, okay, let's say I went 30 meters per second. All right. So in 1 second, I'll travel 30 meters. In 2 seconds, I'll travel 60 meters. And so, in 3 seconds, I'll travel 90 meters. Okay. So that's just the actual distance I'm traveling. Okay. But the velocity is different. It's actually the position at which I've changed. So this just means that it has a magnitude and direction. So I could be going 30 meters per second in a speed direction, but my velocity would be negative 30 meters per second because I'm going to the left, okay? So this is quite important. Positive and negative are to denote directions. Okay. So for usually, you might they might try tricking you with giving you one instead. So make sure to read carefully. But most of the time, you'll be using the standard denotation, which is right over here. So we have positive and negative. So anything to the left downwards is negative, and then right upwards is positive. So that's basically the standard denotation for vectors. But yeah. So just try understanding this. I think a good example of this is going on a highway. So let's say I was, in a car, blah blah blah. This is a parking lot. Let's say I am here. Right? Where you be using obviously the standard denotation. So I was here, and I just started running. All right, I started running, and then there's a speedometer over here. No, sorry. Probably. I think over here. I think this is when I reach max velocity. I mean speed. There we go. 18 meters per second. Okay. So yeah, I'm traveling at 18 meters per second right over there. But remember, that's just the speed. Okay, that's the scalar. It doesn't take into consideration the actual back direction of what I'm going at. So when I'm running, I could be running to the left, right? And so this is where the actual importance of understanding the difference between velocity and speed is, because I could give you a negative 30 meters per second, and then I could switch up the thing in like a small letter, like within a question. And so maybe you don't even understand what velocity is, and you end up with like a negative speed. How could that be, right? And then once you understand, oh yeah, right, velocity in this question, now you don't understand. Are you going left or right? Your intuition tells you left, but if you read the question carefully, you'll know it's right because it's inverted here. And so this is the kind of things that small tricks that they might have to do on you. So yeah, it's just be careful and make sure to understand what's going on. Okay. But that's just basically the wording or like basic understanding. In another lesson, we'll be covering the actual equations and things is that And for the final one, this is an important one actually. All of these are obviously important, but the vectors are what matters. It's acceleration. Okay. So this is a big one, really. Just an important note is that, right, well, first I'll write you down the definition. It's the rate of change in velocity. Okay, it's velocity. Units are meters per second squared, right? Because I'm changing the velocity, that means there's 2 meters per second. Okay. So acceleration equals velocity final minus velocity initial. Okay. And this is a very important factor, is that this is a vector. Okay. So acceleration can be negative, and sometimes it will be negative. So let's say I had and oh sorry, but yeah, I did write it here. This is using velocity. Okay. So this is another important thing. There's a lot of mistakes that can happen if you don't understand what's going on. So let's take the equation I just put down over here. Okay. Let's say, let's take the example actually. My initial velocity, mm, let's say I started off with 20 meters per second. Yeah, I think that should be good. There we go. Okay. So my final velocity was 18 meters per second minus 20. And this equals 2 meters per second squared. Now, you might realize there's a lot of mistakes I have just done. Okay. So I will be covering them. Step number 1. These are speeds. These are not velocities. Remember, I was going to the left? So let's fix that up real quick. I was going at negative 8. My final velocity was negative 18 meters per second. Okay, remember? Velocity is direction. Okay, it's a vector. So I was going negative 18 meters. No, sorry. The magnitude is negative 18 meters per second. But yes, I was at 18 meters per second to the left. Okay. The denotation, remember, negative goes left downwards, positive is upwards right. Okay. So think of it like XY, right? Just like this over here. But yeah, sometimes in the question it will change. But the equation remains the same. It's minus, there we go, negative 20. So my final acceleration would be negative 18 plus 20, which would be plus 2 meters per second squared. There you go. Now, this can be confusing, honestly. But that's just how it is. Okay. Now, let's take into consideration what this means. If my acceleration was positive, yet I was going to the left, which was negative, what does this mean? Okay. What does this mean? I chose this like scenario on purpose, right? This means I was accelerating in the slowing down motion. Okay. I think this is another factor that's quite important. Acceleration doesn't mean you're speeding up. It's the rate of change in velocity. And this is an important thing my teacher mentioned to me, that deceleration does not mean you're slowing down. And I think it's such a common term that people use these days that it's kind of confusing. Okay. You'll have to get used to the fact that acceleration is just a change of velocity. Okay. Over time, obviously. It's over time. I forgot to mention that. But yeah. Time is something that shows everywhere. Seconds. Time is the one thing that's universal in physics. But yeah, let's go back to acceleration. Let's focus on. So in this case, if I was going to the left and I was accelerating at positive 2 meters per second, that means I was slowing down 2 meters per second every second. So this is assuming the actual equation is over time. This is assuming it's 1 second, obviously, right? And blah, blah, blah. Let's imagine this whole thing was 1 second. In that 1 second, I went from 20 meters to 18 meters per second. Yes, so this equation is correct. I was accelerating at positive 2 meters per second because my velocity was going to the left, which was in the negative sense. So be careful. Do not call this deceleration. Okay? Yes, I was slowing down, but in the physics sense, I was accelerating at positive 2 meters per second. Okay. Whew. Okay. So that's all the important quantities, okay, of motion kinematics. So let's review. Linears and vectors. Linear scalar can be negative. Take temperature, for example. Vectors are magnitude and direction. So that's important to keep in mind. The position is an object's location in space. You have to relate it to something. That's a vector. Distance and displacements are the scalar and vector versions of the actual like lengths and paths of travel. Displacements is the change in position. This distance is just the total length. So, try to remember the track path. That one was the one that made me remember. And also the linear line over here, the number line. This one is good to know because it can teach you quite easily what the difference is. Then we have speed and velocity. They both use meters per second. Okay. Speed is just the rate at which distance was traveled. So think of like a car, it's going at 45 meters per second. And then, yes, its velocity would be the actual speed, it would be the same. But let's say I was going 30 meters per second backwards. Guess what? My speed now is 30 meters per second, but my velocity would be negative 30 meters per second. That is because my position is changing in the negative sense according to the denotation right over here. Okay. So just remember scalar and vectors. Practice, practice, practice. Then we have the differences in speed right over here, then the velocity. Okay. Then acceleration, just remember this can be extremely tricky. The problem I just chose is kind of a confusing one, and so we'll be practicing that later on. And so yes, just keynote over here for acceleration kind of is that positive and negative. I just like I showed here, yeah, it does not tell us direction. All right. It doesn't tell us direction, but how the velocity is changing. So plus a negative, so those senses does not tell us the direction velocity is changing. All right. If you're confused, I just mean that it does not tell us what direction it's going. So, for example, since this is positive, right, it does not tell us that velocity is going to the right. It's just telling us at which rate velocity is changing. Okay. So to further deepen into that, is that it just doesn't mean speeding up. So positive and negative doesn't mean speeding up or slowing down. Okay. This is important to keep in mind because you'll come across very tricky problems with acceleration. It just depends on the direction of the velocity. It depends on the direction. This is important because remember, velocity is a vector. So the magnitude will be the same, but the direction is what comes down to. Right? And the acceleration only takes into account the velocities, in physics at least. You can still have normal acceleration, but it would just be the same as velocity except without a direction. Right? So, for example, this is a very simple thing, and actually, I think I might just talked about it now. Is the universal acceleration? Well, not universal. Sorry, the global acceleration in planet Earth is gravity. Okay, gravity equals negative 9.8 meters per second. Right? That's using standard notation, of course. It can be backwards. Okay, so G is gravity, and it's 9.8 meters per second. So now let's just do one example problem before we finish the video. So, example. Let's say I threw, so this is my hand or whatever, this doesn't matter. I threw a ball up into the, here we go. I threw a ball, boom, upwards. Simple as that, straight upwards. Let's say I threw a ball upwards. What do you notice? And you can try this in real life. Throw anything upwards. I'll throw my pen upwards right now. All right. What do you notice about that? You'll notice that, with the force or speed you gave it, the velocity really, is that it's going upwards, okay? That's because it's positive. The velocity is positive. Boom, 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 boom. The velocity is going. But then you'll notice there's a point right at the top where the velocity equals 0. But why is this? Why does our pen actually come down? Why does it not just stay going upwards? Okay. A lot of people will just say gravity, but they never really understand how and why this works. This is because gravity is the negative acceleration, and in our sense, right? It's the acceleration that pulls us downwards. Okay. So the velocity will be going upwards, but then the acceleration, in this case it's negative, will be going downwards. And so this creates a status where, let's take right here an example. Let's zoom in, okay? Boom. Let's zoom in right at the spot right here. The time can be like 2 seconds, it doesn't matter. The velocity, your velocity, the one you gave it to the object you threw up, is pretty fast, okay? It's faster than gravity. It's really fast. It could be like, I don't know, let's say gravity was just 10 meters. You can estimate to 10 meters per second. On the exams, you will estimate to 10. It just makes life easier. Let's say the velocity was 20 meters per second here. So then you have gravity pulling down and 9 to 10 meters per second. Yeah. So your velocity is stronger than the gravitational acceleration. So that means it will go upwards. But then it keeps going upwards and upwards until the very top. What do you notice at the top? It starts falling down. But if you look at the singular time frame, you'll notice that both the acceleration and the velocity equal, right? This is called equilibrium. This is the point at which the velocity and is 0, okay? This means the acceleration has basically just slowed it down, okay? This is important. Just because it's negative doesn't mean it's slowing it down. Just because they're in opposite directions, that's why it's slowing down. Since velocity is going upwards, and well, not up, you know what I mean, upwards, and then the acceleration or gravity wants to bring it down, okay, that means it will slow it down, okay? So once I throw it up, okay, gravity is always trying to bring it down. It's not something that acts just one time. It's the whole path, just like I mentioned here. This whole path, right, or like right over here, all the time gravity is trying to pull it down, pull it down, pull it down. Okay, but then we throw it up, and so at the top, that's the point at which acceleration, the gravity, slowed it down so much to where it's 0 now. It's basically at a point of just no movement. Okay, and this is a very short time frame, obviously, because in real life things happen fast. And so now it will start falling down. And guess what? It will, this acceleration, right? It means that it's the change in velocity. So if something is accelerating downwards, that means the velocity will start changing as well, going downwards. That's why, that's why when it goes up and down, it comes down fast as well, right? Because now the acceleration is pulling it downwards, the velocity is going downwards too. Okay. Now we'll touch up more on gravity, but this is just a very simple example. And so, in case you're curious about the times and stuff like that, you can have this, and as long as it's perfect, you can test this as much as you want. It will take the exact same amount of time you throw it upwards for the thing to or object to fall down. Yeah, and that's because of just gravity. You know. So if you threw something up for 2 seconds, boom, falls down same amount of time. Okay. So yes, I want to thank you so much for watching. Please comment if you have any type of questions. I'll try answering them. And this is just it for introduction to kinematics. And thank you so much for watching. Have a good day.